Hello and welcome back to the Trivial Pursuits of JUG and RTDL. This is episode 2 of our Gödel, Escher, Bach discussion. This is
JUG.
And I'm RTDL coming at you from Central Texas. Where are you coming at us from, JUG?
I'm coming at you from Northern California, north of San Francisco.
That's awesome. All right. Well, before we get started with our second chapter of Gödel, Escher, Bach, I got to ask you what you're drinking today.
Oh, today I'm drinking from Chico, Sierra Nevada, Electric Torpedo. You?
And dad beer. I got a dad beer too.
Good.
That's Centennial IPA from Founders.
Nice.
So well, I guess I need to get a Texas beer in here every once in a while. But I do have a Texas beer glass. It's a RAR. So
I do like raw. It's good.
Good. They're still around. Okay. So let's get started. I'm going to put on this Chopin's Etude, but I wasn't prepared. So as we get into this 2-part invention, that's the dialogue. Listen for a minute. All right, I like it. So the dialogue is 2-part invention, so it just involves Achilles and the tortoise. So do you want to get into what the dialogue's about?
Yeah, it starts out about the race. So they're at the end of the race and they've just said, okay, so that wasn't true because Achilles does make it to the end of the race. And so he sits on top of the tortoise and they start talking about propositions and conclusions and how to reason and when is something true and what is a formal system, basically.
Yeah, and they're just basically talking about reasoning about reasoning about reasoning about reasoning.
Right. So it's all the different levels.
Yeah, but the tortoise offers 2 proposals and 1 conclusion, and he challenges Achilles to convince him, being a tortoise, that this conclusion follows from these 2 proposals, and Achilles tries, and it ends up, the tortoise keeps introducing another level of reasoning to be convinced, and it ends up just being an infinite task. And
Right,
Achilles
so-
basically is crestfallen. He has he's writing his stuff in a notebook, and he's filled the notebook up, and he's just ready to fall on his sword.
So it's actually pretty simple to state the first 2 levels. So here's a statement. Statement A, things that are equal to the same are equal to each other. And to me, that means the same value, maybe. So if 2 things are equal to the same value, then they're equal to each other. Is that what you get from that one too?
That's what I get, yeah. You could, or like an isosceles triangle, I guess.
Right. So congruent. Yeah. So then then he does talk about triangles, and so that's statement A. Statement B is the 2 sides of this triangle, so a specific triangle, are things that are equal to the same. So he's saying that the statement is these 2 sides of this one triangle are equal to the same.
Mm-hmm.
So they're equal to, they're each 5 centimeters long, for example. And then the third statement, which he jumps to statement Z, knowing full well what he's doing, he says, here's the third statement. And it says, the 2 sides of this triangle are equal to each other. Okay, so that's a statement. You have to think about them all in isolation, basically, until the last one, which is making a statement about the actual triangle.
Right. He wants Achilles to prove that Z follows from A and B being true.
Which, if you think about it logically, it makes sense. If 2 things are equal to each other, to the same value, then they also must equal to each other. And if the 2 sides have the same value, then the last statement says that they're equal to each other. And I know it sounds like I'm speaking in circles, but then he says, what about if the statement C if you take A and B to be true, then statement Z is also true. So I think that's something we can believe to be true, right? So if A and B are true, then Z is true. That's the statement.
Mm.
But then his point is, well, then prove that statement to me. And then he
Yes.
says, but does that mean that Z is true? And then it's he can say, then what does he do after that?
He says, well, if that Z is true, then I can say that there is a statement D that says if A and B and C are true, then I can add D to the end. So then now
And
it's
D,
A plus B plus C plus D lead to Z. And then it keeps
right.
adding on an E and then an F and just never stop. And I think that's Hofstadter's trying to point out some flawed logic.
I think what he's also trying to do in this dialogue is to say that language is complicated.
Mm.
And he's the point of making a formal system is to declutter some stuff because language is very complicated. And then what we're going to see is that if we want to we're trying to formalize not all of language just yet, but just numbers. So
Yeah.
maybe that will make it easier.
Yeah, he says that later in that the interpretation of symbols of a formal system are really the key. Perceptions of isomorphisms create meaning in the minds of people, and that's what Hofstadter said early on when you were talking about the preface to this edition. Is that he's trying to get to formal
Hmm.
systems in consciousness
Right.
through isomorphisms.
Hmm.
Anyway, I got ahead of us there, but so he introduces a PQ system that in this chapter. And you're the mathematician here, so I'll let you explain that.
Well, you're gonna put it up here, I imagine,
Yes.
but it's so it has two rules.
Has a definition and a rule.
Right. It says the definition so first of all, you only had three symbols. P, Q. Remember the MIU system? It just had M's, U's, and I's. And
Hmm.
this system called the PQ hyphen system has three. It has P, Q, and a hyphen. And the definition that it gives is that if you have, and it uses X as a variable. So if you have X, P, hyphen, Q, X, the same X, and then hyphen, that is an axiom where X is any number of hyphens. So just choose any number of hyphens and you can have X, you'll probably see it here, X, P, hyphen, Q, X, hyphen is an axiom. So remember, axioms is what we build on to make theorems.
Hmm.
So then the rule that's given, it's a little complicated, but it says, suppose X, Y, and Z, so you have three variables here, all stand for particular strings containing only hyphens. And suppose that you have X, P, Y, Q, Z. So this is some number of hyphens in between and before P's and Q, P and Q. Is if that's already a theorem, then you can make a new theorem by adding or putting a hyphen after the Y and one hyphen after the Z.
Yes. And just a quick review on this and what axioms, what these terms mean, because I assume probably most people that would watch this might know, but in a formal system, theorem doesn't mean exactly the same thing it does in a mathematical
Right.
proof. So theorem in this context is a produced string, a string producible in a formal system. That's all a theorem is. An axiom is a theorem, but it's a theorem as a source of all other theorems. So like the axiom schema is the most basic axiom. And
And
then
usually
go
take
ahead.
axioms to be true, and the rules are just what you place upon the axioms, and
Yes.
then you produce a bunch of theorems. basically.
So yeah, and so then it goes to bottom up versus top down, where you can work from one way. You can go bottom up, working way up from the basics to larger strings, or you can get a really long string and try to work your way back to the axiom schema.
So then if you start producing strings or theorems, which are the same thing, the strings, using this rule, I think you quickly come to see that it actually does have some meaning to you, to us. And that meaning is it's really just another way of writing addition. So if you start with the rule says if I have a theorem, then if you add one hyphen to the y and one hyphen to the z, that's also a theorem. And what that is telling you, if I know a true statement, for example, I know that 2 plus 3 is equal to 5, then if I add another hyphen to the 3 and another hyphen to the 5, then 2 plus 4 is equal to 6. So you get a new addition statement. And the way we do that is by interpreting. So we're interpreting the symbols in a different way. And what is the interpretation that we're actually doing?
So there's an isomorphism that we make as human beings. We say that, that reminds me of addition.
Mm-hmm.
And then so we assign ideas or names to these rules.
And the other interpretation we're doing is it's so obvious, but you have to state everything that if you have a string of hyphens, then the number of hyphens, that's we're going to relate that to an actual integer, a number, a positive integer.
Yes.
And so the definition, if you go back to it, it makes sense now. It says x p hyphen q x hyphen, which is just saying if I have a number x and I add 1 to it, it's equal to x plus 1. So x p hyphen q x hyphen is just x plus 1 equals x plus 1.
Right. Well done. Somehow you can look at that and notice that addition is there, and you create a meaning in people's mind. And that's a very important point that Hofstadter is trying to make with this chapter that's going to be important later in the book, all throughout the book. But he does mention something in this where we're talking now about how isomorphisms induce meaning. And he mentions this book, The Decipherment of Linear B by John Chadwick. And it's an example of how they use isomorphisms to basically crack the code of linear B.
The isomorphism that we're looking at and what we're trying to get to here, he's trying to get to, is it's literally just strings, P's, Q's, hyphens. That's all that you're looking at. So you could have 1,000 hyphens and 1,000. You just put just one P and one Q because it's just plus and equals. So you can add any two numbers you want to in this system, and you can get the answer. So you can imagine, and which is what I imagine. Sometimes when I think about Alan Turing and his computer system, which is just ones and zeros. So there would be another level where you'd have to take the ones and the zeros and translate them to P's and Q's and hyphens. There's that one step. But then once you've done that, you're just feeding, I think of it as just a strip of paper that just has ones and zeros, and there's just a machine that's reading each number as it passes by, and then it spits out the answer. So you get two numbers and it'll spit out the sum.
Card reader.
Yeah, it's like a card reader, yeah. And so that so you're jumping from a very formal system with just symbols into something that has meaning to all humans, which is addition. So addition is really a basic thing that you can just put out in ones and zeros, in this case P's, Q's, and hyphens, and you get out the whole addition system that we know we've learned since we were young.
Yes.
Since we're kids. So there's a
Yeah.
jump there, and that's where he's getting to the meaning from the symbols.
Right. Yeah. So these theorems, they correspond to real world truths. You can map them into things that we think we understand, like addition.
Right. And he formalizes a whole system like math, like arithmetic. If you can get multiplication, addition, if you can get a lot of stuff out of numbers in a system, then he's going to show that you have natural paradoxes that come up all the
Yes.
time anyway. So that's what we're building here.
Yeah. And then he goes on to active versus passive meanings. And in this section, he says this is probably the most significant fact of this chapter. So I do want to read it. It's, if it's understood deeply, is this: the PQ system seems to force us into recognizing that symbols of a formal system, though initially without meaning, cannot avoid taking on meaning of sorts, at least if an isomorphism is found. So he wants us to focus on that.
So where does meaning come from? Where does it arise from? He's getting us ready to make this leap to consciousness. I'm a little shocked, like we talked about. We started this about 3 years ago, and I got bogged down in all the calculations, but I didn't really get what I'm getting now, which is the connection to consciousness, and that's the whole point of. Actually, I think
Yeah.
that's his huge thesis, which is right here. He's talking about it right here again. I don't know how I missed it the first time. I guess I wasn't looking for it.
I guess so, yeah. Yeah, because he definitely hits on it. And so he goes on to say that an interpretation will be meaningful to the extent that it accurately reflects some isomorphism to the real world. And really what he's saying here is, can all of reality be turned into a formal system? Basically, he's asking if the universe operates deterministically.
Right, which is a huge question in certain areas. Are our lives determined? Or do we have choice? That's
Yeah, there's a guy, Robert Sapolsky, who's been trending lately. He says that that everything's predetermined.
I think I lean that way too.
Okay. I'm not gonna take a side on that.
He starts talking about mathematics and symbol manipulation, and I taught math very many years, and
Yeah.
this is the thing I try to get across, which is you're just algebra is you're just manipulating symbols basically, and if you can manipulate those symbols, then you get it. I mean, even if you don't get it, you
Yeah.
can do it by just manipulating symbols.
If you
I think
follow the
so.
rules, you will get the
Yeah,
right answer.
right. You'll get x equals the correct answer, following the rules using symbols, and then
Right.
that's a big jump. I mean, it's not an easy concept to get across. And then you want it's actually very interesting the example he gives, because it reminds me of me. He talks about what multiplication. So when you multiply 12 times 12, we all know that it's 144, and we don't need to draw out a box that's 12 by 12, cut it into all its squares, and then count up the squares. We just know that 12 times 12 is 144. We've learned that.
Yes,
Or
but
we
that gives us a way to verify our calculation. We could do a 12 by 12 grid and count. So,
Right. And we all have to believe that. And then
mhm,
he jumps to a huge number. What about
mhm.
nobody could ever draw a rectangle that huge and count the squares? That's an impossibility. So we're jumping to believing that that we can get that using symbol manipulation, but we would never get the correct answer by counting the numbers. So even if he said, even if you hired a bunch of people to do it, however long it took, months, years, whatever. Even them counting it, you're not guaranteed they're going to get the right answer because they could have an error. They could make it just one little error, which everybody I know that has ever done math, which is everybody, you
Mhm.
always make errors. People make errors.
Every single
So,
day.
especially in counting things, I mean, you just get lost after a few just count. But
Yeah.
anyway, we're looking at symbol manipulation that gets around the we're not getting to infinity yet, but we're getting to very large numbers.
But we believe that this process holds for all numbers, but we
Right.
can't. How can you prove that? And I think that's what
Right.
Hofstadter's trying to show us.
Exactly.
Well, we're taking this leap of faith, and you've been indoctrinated since birth, really. That
And this goes back to the dialogue. You just like instead
Mhm.
of adding another line of, if A, B, C, D, E, whatever, he's adding just another number. So you had to go to the tens, the 20s, the
Mhm.
30s, the 40, I mean not the hundreds, the 10,000s, the millions, the billion. You just keep making your numbers longer and longer. How do you know that this symbol manipulation will always work?
And his
Because
contention that is
yeah,
through reasoning that we
right.
believe it through reasoning, and we'll get into that a little bit later in the chapter. But why do all these basic laws of arithmetic seem to hold up? And why do we believe the answers we get with big times bigger or that kind of thing? Things like counting and, associative property, all this commutative, distributive, all that. We just assume the process holds for all numbers. And I think Hofstadter is like, well, how can you know that? They're not verifiable because we can't test the infinite with finite means. And
No.
it goes back to what Gödel said about using a reasoning system to prove its own self.
Right, yeah, you can't do that either, so
Yeah.
you there's just lots of levels. It's another circular thing here. He's saying, "We know that we could take any number, any two numbers, draw a rectangle, count the squares, and that would be the products. We know that to be true. But then once you get these huge numbers, we can't do that. So we go back to just symbols. I know how to multiply. I know how to show you how to multiply two long numbers. It would take a long time, but I could show you step by step how to do it, and we'd get to the true answer. But then, so but that has nothing to do with the actual counting of squares. The symbol manipulation is a totally different thing than counting squares. Yet we get the same answer. That's the isomorphism. So we're
Mhm.
going to not, I mean, when you're learning to multiply, you do count squares, and then you go to the symbol manipulation, and then you really don't look back. Now it's really just this. It's just
Yeah.
symbol manipulation. So we've turned a concrete counting object, counting, A times B, into just symbols, and then that's what we think of as multiplication.
Yeah.
Yeah.
So finally, he mentions Escher here. Operation, so I'll put it up there so we can see it. But it's just demonstrating the contrast between the formal and informal with a transition region.
Okay, and then after that, he goes into one of the most famous proofs around, which is the Euclid's proof of the infinity of primes,
Mhm.
and he actually goes through the proof, which we could
Yeah.
do here. Okay, so you so you take you take any number, take a number, n. Now you could once I have a number n, like think of a big number, 100. I could take every number before 100, 1, 2, 3, 4, multiply them together. So I get 1 times 2 times 3 times 4, all the way to 100. And that's a big number. It's a huge number. But what the reason Euclid made it this way was because you're guaranteed that every number before 100 will divide evenly into this huge product. So what he's going to say next is, well, if you add 1 to this number, then I'm not adding 1 to 100. I'm adding 1 to the product of 1 times 2 times 3 which is a lot bigger number,
Hmm.
then that number has to be at none of the previous values can go into that sum, so that number has to be prime. So there's a bigger prime number than n. So then just make, and this is the infinity leap. This is the reasoning leap. Just think of n as the biggest prime number. So suppose there is a prime number that is the largest prime number. Just just make that number n, and then do the same process, and then but you find another prime number. You take the product, add 1 to it. That's another prime number, which is larger than the previous prime number.
Again, and we believe it because of reasoning. We could never check that it's true,
No,
but maybe not even, even when we get quantum computers, there will still be a
no,
larger prime. I
yeah.
believe, but I only believe it
Well,
because of reasoning.
yeah, but yeah. They do other interesting things with prime numbers now, like how many
Oh,
two
yeah.
two prime numbers that are doubletons, or they come back to back primes. Are there
Okay.
infinite number of those, or how far is it between each prime? They want to know how many primes there are. What's the limit of prime? I mean, they're always thinking about prime numbers. When I say they, these certain mathematicians that
Mhm.
study number theory, prime numbers, and I've been watching some videos. They're doing a lot of very interesting math with that. And you know who also comes up in these videos is Ramanujan. He comes up a lot,
Okay.
and it's very interesting. I'm This is another reason I'm really enjoying going back to this book, is because I can I find stuff on YouTube to look at too. So it's really easy to go to these little rabbit holes, but just to me, it's fun.
It's a lot of fun.
I,
Well, so that's Euclid's proof, but the thing about the proof, it doesn't treat each case separately, but
right,
in general, with this concept n factorial plus 1, it suggests that there's always a larger prime, but it's representing infinity with a finite, finite
right,
structure.
right.
So so you can say that all n, well, what is all n? It sounds like a silly thing to say, but I think Hofstadter's not afraid to say it. So
Yeah,
effectively, proving infinity means you have to be able to do it with finite means. And Hofstadter's asking that question. I think he's setting us up for something to come, some
right,
reasoning,
right.
some reason
And
why we can't.
he's getting to that, the when you do build your formal system, you can have the underneath just the basic axioms and theorems, addition, subtraction, multiplication. But then you go to the next level where you're gonna have, where you do have for all numbers, for all this, or for every this, or so you're these words, have meaning. This is where
Mhm.
you bring in the English and the math together, going back and forth. Two levels. Remember, we are talking about the two levels last time. Forwards or up and down. Both are equal. We do them at the same time, which is what makes us,
Yeah, bottom down, top up.
yeah.
Yeah, and he ends the chapter basically saying, generally, just what you just said. We tend to equate meaning with the familiar patterns, and thereby we infer rules from that.
Mhm.
But we're guided from birth to do such things, and I think he wants to question that. He says that he does like to question everything, and I think he's going to question that reasoning. I call it indoctrination. That's
Right.
what it is.
And and then he this is where and then this is what I was talking about before, where he takes Euclid's proof, and what he's claiming that when Euclid came up with this proof, he probably had a lot of neurons firing to get to this proof, which is as equally complex as the proof itself. So
Mhm.
even though I said the proof and you can see it, it's not very many steps. What he's saying, there's lots of actually many steps going on behind the whole proof. So there's lots of, and these little mini things that are happening that we don't see, we're hardly aware of. when our brains fire, where you're shooting so many neurons, making connections, etc. It's just as complex as the proof that you're solving or coming up with. So this is that other leap, the leap to consciousness.
Yeah, our thought processes are more complex than we think they are. Everybody's saying.
Right.
So turtles all the way down.
Exactly. Turtles all the way down.
The neural
Which,
reactions. Anyway,
which
that's
is,
that'll be the title of this episode, Turtles All the Way Down. So I think we got
that's
to
what,
chapter 2.
yeah. It's a
Pretty good
nice,
time.
sweet. Yeah, it's hard to get Bach into everything, but he's in the title, two-part invention. You should listen to it.
Yeah, maybe I'll throw on some Bach here after we get done. So I guess we'll wrap this episode up. So join us for the bridge to episode 3. That's the way these are structured now. You're gonna have a dialogue and then the
Right.
chapter 3. So
And we will read a dialogue, like we
yeah, and
promised.
maybe we can just take excerpts if it's too long. But
Yeah.
some of these are pretty long. Just the one this week had a lot of symbols in it, so it wasn't really readable. But yeah,
Right,
maybe
right.
I'll check next week's out. Okay. We'll try to release these on Friday. It's going to be hard each week, but we'll try to keep to that schedule. All right. So that was a good episode. We'll
Oh, and
see.
if you haven't, push the follow button.
Oh, yeah.
Push the follow.
Please follow us.
Or do you like it, or whatever the buttons you want to push them all.
Push all those buttons. All right. Have a great week. We'll see you next time. I'm RTDL.
And I'm JUG.
Bye.